All right, so we're going to finish up this week by looking at 5.4 part 2. We'll do that, and then we'll take a look at 5.5, which is on graphing logs. Okay, so really just the end of logarithms. And that's going to pretty much wrap up everything that we're going to study in algebra for this class. So at 5.5, that ends the chapter, and then when you come back next academic week, which is a couple weeks away, we'll be looking at chapter 6, which starts trig. All right, so let's just start out with a problem that wants us to rewrite that using properties of exponents. So when we rewrite it, we're going to have separate things. It's like we have one exponent altogether. I want to separate that out. We've already done this kind of thing with logs, okay, separating it out. This is just separating out exponentials. So when we're done, we're going to have a to the x's, a to the y's, and a to the z's. All right, let's start with the plus and the minus. What's the rule for addition? When would you add two exponents together to get an answer? Add two exponents together to get an answer, because that's somehow there must have been something before that, and the step was to take the two exponents and add them together. Yeah? It does have to do with something that's the same, but not adding. There wouldn't have been any addition in the original problem that would have caused that plus sign. Yeah.
Is it when you're multiplying?
Yep, when you're multiplying things with the same base. All right. So if I had a to the 2x times a to the 3y, the answer to that would be a to the 2x plus 3y. Right? So I just separated it out with the plus. And then how about the minus? When would you subtract in the exponent? Chris?
When you have a division.
Yeah, when you divide. So that would have started to come from that. Okay. All right. Now the bottom looks good to me. It's in terms of a to the z. But the top isn't. It's a to the 2x, a to the 3y. Well, 2x. Tori, what operation are we doing with 2 and x there?
Multiplication.
Multiplication. So now we have an exponent with multiplication. When do you multiply exponents together? When you have a what? Yeah?
Power to a power.
Power to a power. So a to the 2x must have been a to the x squared. Now I have something in terms of a to the x. Okay, so now that's good. How about a to the 3y? How would you rewrite that one? In terms of a to the y, and then you can do something to it, but it's got to be a to the y. And then something else. Yeah?
A to the y cubed.
A to the y cubed. All right, so now we've written that in terms of a to the y, and the bottom is fine. It's just a to the 1z power, so it's already good. That's it. So just having you practice using your rules of exponents to simplify and separate something out in terms of a to the x, a to the y, and a to the z. Any questions on that? Okay. So now we're going to look at how we can solve the kinds of problems we did graphically, like half-life and bacteria doubling, but we're going to look at the same problems algebraically. Okay. At this point, you pretty much should already know like the formula. We're going to have to just go through how do we get the variable by itself. So we've already done this problem. We did it, I think we did it on Monday or Tuesday. It's an exponential growth problem. But if you're wondering why we're looking at an exponential growth problem in a log section, because to solve exponential growth problems, you have to use logarithms. All right, so the problem is you get an initial population of 50,000 people going up at 2.5% a year. How long will it take for the population to hit 100,000? All right, what's the first thing I have to do before I even have something to solve? What do I have to set up? Yeah,
The equation.
I got to set up an equation. So our equation, we usually do something like an amount as a function of time, or population, so I use P as a function of time. And Jarek, in the exponential growth formula, what's the first thing you start with? Or exponential decay. It's actually the same thing.
The initial amount.
Initial amount. What's my initial amount here?
50,000.
Yep, 50,000. So 50,000 times, and what's the expression that goes in the parentheses? You don't have to tell me even yet for this problem. Just in general, it's something plus something. Yep.
1 plus r.
It's 1 plus r. So in this problem, my rate is 2.5%, but as a decimal, that's 0.025. So 1 plus 0.025, you're going to put 1.025 in parentheses, and then your exponent is t. How many? That's the time. Okay, so there's your formula. Now, they're asking how long for the population to reach 100,000. So Gabe, where does the 100,000 get plugged in? We've got two choices.
The P.
What's the whole thing? We're plugging it in for... So your two choices are P of t and t.
Yeah. So P of T.
P of t, yeah. We're going to plug it in for that whole thing. So the P and the T, both of those are going to be gone. So fill in 100,000 equals 50,000 times 1.025 to the T. Now, what makes that problem a little harder that I probably wouldn't give something like that in Algebra 1? I mean, there's not a lot of numbers in it. It's not like even a distributive property. It's what's in there that makes it harder. Yeah?
The variables and exponent.
Yeah, you've got a variable in the exponent. So we have to figure out how to deal with that. All right, so I want to get t by itself. Does anyone see something I could do first to start to get t by itself? Yeah,
Divide each side.
yeah, we can divide each side by 50,000. Because remember, the goal is to get what's in that box alone. You have something in front of the box that's multiplication, so let's use division. So 50,000 and 50,000. Okay, 100,000 divided by 50,000, 2. So 2 equals 1.025 to the t. At this point, there's no more adding, subtracting, multiplying, or dividing that you can do. It'd be nice if that wasn't in the exponent. Okay? If I just had it in front, that would make it a lot easier. Now, we have a rule for when we can move it in front. You can't just move it in front the way it is right now. You can't just say 2 equals t times 1.025. Okay, you can't do that. But when are you allowed to move the exponent in front? You had what kind of problem?
Log.
You had a log problem. Okay, so let's take the log of both sides. So take the log of what's on the left. Take the log of everything that's on the right. Now you're allowed to put the t in front. Okay. A log, it's just a function. It's like square rooting both sides or squaring both sides. You just took the log of both sides. All right, so now we can write log 2. Don't worry about what the log of 2 is. We're not going to figure that out till the very end. Equals t times log 1.025. So now the equation you have there is basically just something like this. A number equals a letter times another number. Okay. The same operation you would use to get x by itself here is the same thing you would use here. So what would I do on each side now in my log equation to get t by itself? Well, Justin?
I do that now.
All right, how would I get x by itself there?
By dividing both sides by 5.
Yeah, and this is the same thing. Number, number, equals, letter, letter, number, number. So it's exactly the same thing, except it's not the same number.
Yeah.
So how do you think you get the t by itself?
Divide both sides by the log of 1.025.
Yeah, exactly. Divide both sides by the log of 1.025. Log 1.025 is just a number. What number is it? I don't know. I'm not really worried about what it is right now. And divide by log 1.025. And there's your answer for t. Okay. We'll type it in and see what we got. So I've got log of 2. Make sure you close the parenthesis because I'm done with that argument. Divided by log 1.025. So we get an answer of 28.07. And that is measured in what unit? Years. So it'll take a little over 28 years for the population to double. So let's go back down. 28.07. Any questions on that? All right. I just want to check something real quick. 28.07 divided by 2.5. Yeah. There's shortcuts to figure out how long it would take something to double without using logarithms. You can kind of approximate it. And people used to do that. Like if you said, all right, I'm going to put $5,000 in the bank today, and I'm never going to take money out. How long will it take for my money to double? That's kind of a common thing. So there's shortcuts to figuring that out. If they had changed this like to 110,000, then it would be a little different. It's not as common of a problem. This was a population doubling. But the logarithmic approach will work all the time. It doesn't matter if it's doubling, tripling, increasing by 2.6 times. Logarithms always work. So I'm not really going to show you specific shortcuts for like certain cases. Okay. We'll just stick with that approach. All right. If you were going to solve it graphically, you would end up graphing what's on the left and what's on the right of that equation, and then what would you be looking for? You'd be looking for an intersection. And we did that exact problem a couple days ago. Okay, same numbers and everything, same answer. All right, so we're going to talk about how we can model data with an equation. Now, in Algebra 1, probably Algebra 1, you might have like a set of data. It looks something like this. And you might try to find a line that fits the data. Right? If the data looks straight, you try to find a line that fits it. And that's called a line of fit. Now, in statistics, if you take statistics, you might talk about a line of best fit, which is, it's not an approximation. It is the most perfect line you can find to fit that data. Okay, it's like the best one possible. The points aren't perfectly straight, but you're finding the best line you can. Well, a line of fit wouldn't really work well here. Right? This data is curved. Could I find a line of fit? Sure. Maybe it would look something like that. That looks like it's kind of near all the points. The problem is if you use this line to predict what's going to happen later on, it's not accurate at all. Okay? It's kind of accurate in the early part, but then it's not after that. So we would want to find a curve, like the best curve we could fit to that data. Okay? And there's different kinds of curves. There's parabolas. Maybe like a parabola would fit that pretty good. It depends. Okay? So we're going to look at a specific kind of curve, and it's called a power function. So usually you have to find the A and you have to find the M. So what ends up happening in a power function is it's a polynomial. It could be a parabola if M was a 2. It could be cubic if M was a 3. All right. Okay, but it's called a power function. One thing we have to figure out, though, before we just start typing data into the calculator and finding a power function, is we have to figure out, is our data, is a power function even the right thing to try? Right? So first we have to figure out whether or not a power function is the right thing to kind of go after. And then if it is, we have to figure it out. Okay. All right, so let's start with that equation. Okay, I'm going to go through just a few steps, and I'm going to hope you see a pattern and something it looks similar to something you've seen before. Okay, I'm going to start with that. And what I'm going to do is I'm going to take the natural log of each side, just like we did in the last problem. Just taking the logarithm of each side. Okay. And I chose to use the natural log in this case. So I get the natural log of y equals the natural log of ax to the m. Now, what could I do with that m? Now that I have a log equation, and that m is an exponent in the argument. Yeah.
Move it to the front.
Move it to the front. Even if you're not sure what's going on, why is he doing this, eventually you're gonna notice something. All right. So I can move the m to the front. That's one thing I can do. The other thing is, think of that's multiplication. A times x to the m. If I want to take that log and split it into 2, how does multiplication split? Is it a sum or a difference? Yeah.
Addition.
Addition, yeah, it's a sum. So I'm going to do both things at the same time. I'm going to put the m in front, and I'm going to split it. Actually, I guess I do it in 2 steps. So I'm splitting it as a sum. ln of a plus ln of x to the m. And now I'm going to take the m and put it in front. Okay, when I did that step, I also changed the order because I think it'll make it a little more obvious what I'm trying to get you to recognize. So I have m ln x as one of my terms, and then ln a as the other one. Does anybody recognize what that kind of looks like, that last line? Yeah?
It looks like the slope form.
It kind of looks like y-intercept form, right? Where you have a slope and a y-intercept. If you cross out the ln's, don't do it on yours. But it looks like y equals mx plus, we normally use b, but y equals mx plus a constant, right? So the fact that this kind of looks like the y equals mx plus b equation, which is a straight line, that's going to be a hint as to how we figure out if we should use a power model. It's going to have something to do with logarithms and looking like a straight line. Don't worry about that. We're not going to add that. All right, so we're just going to stop with that. All right, so again, that's a hint at what we're going to have to do. So determine if a power model fits your data. Okay, if that's the right type of thing you should be looking for. The first thing you're going to do is you're going to take the table of data they give you, and you're going to take the natural log of every single number in the table. So you're going to have an original table with x's and y's. You're going to take the ln of every single number in the table and just make a new table with all those numbers. Once you create that new table, you're going to graph the points in that new table. You're going to graph them, and you're going to see if they look like a straight line. And that's going to tell you whether or not you should use a power model. Okay, if you graph all the points that you took the natural log of, and they look like they're in a straight line, okay, kind of like this equation looks kind of like the line equation for a line, that's going to tell you you should use a power model. Okay. If you graph the points and they don't look like they're a straight line, then you would stop right here. Then you wouldn't go any further. All right, but if they look like a straight line, the next thing is find your b, which is kind of like your y-intercept, and then find your m, which is kind of like your slope. Did I use letter B? Let me just double check. I used A, so I should stick with the same letter. I put B because we're used to thinking of B as the y-intercept, so that was my fault. I used A and M. And then once we have A and once we have M, then we can write the final answer. Plus, you know what? I'll show you an example of the final answer after. Don't worry about that. Okay, so it seems a little weird at first, but once you go through it, it's not too bad. Okay, does everyone have those 4 steps? All right, so let's see if I think I have an example right here. So we're going to determine if a power model is appropriate for the data I have in this table, and if it is, then we're going to find the model. Okay. And by model, I mean like the equation. All right, so step 1 is to take the ln of every number in that table. All right, so I'm going to make a new table, and this is just a temporary table. You're going to use this new table for one thing. You're just going to see if it looks like the points are in a straight line. If they are, then you're done with the table. You can get rid of it. You never need it again. ln x, ln y. Okay, so we'll just go through and take the ln of all those numbers. So ln of 1 is 0. Ln of 3 is 1 point. And again, we're going to graph this, so you don't have to be super accurate, because if you're graphing by hand, you're not going to be able to graph to like the 100th. Right? You're just going to roughly get a sketch. So it's about 1.1. So 0, 1.1. ln of 5 is about 1.6. Okay, and ln of 8, let's see, is about 2.1. Okay, and now let's do the bottom row. Well, ln of 5, I already have that one from up above. So that's 1.6. I don't have any of the others. So ln of 31.2 is about 3.4. ln of 73.1 is about 4.3. And the ln of 160 is about 5.1. Now, I said you should graph it, but you can kind of tell by looking at a table if something's going to be in a straight line or not. If you see a pattern to the values, if they're going up by kind of close amounts each time, You can go by that. If you don't see a pattern, you can just sketch it. Okay, so let's sketch it and see. All right, so my first point is 0, 1.6. About right there. My next one is 1.1, 3.4. So 1.1, maybe about right there. 1.6, 4.3. So 1.6, 4.3. And 2.1, so a little more than 2, a little more than 5. A little more than 2, a little more than 5. Okay. Does it look like those points are in a relatively straight line? Yeah. So at this point, you're done with this table now. It served its purpose. It told you that your points look like they're in a straight line. So a power model is what we want to use. Any question on that? All right, so now we want to figure out the M and the A. Which one you do first, it kind of depends on the problem, but let's look at ours and see. Bless you. Okay, so now I'm going back to my original table of data. All right. I would pick, you got to plug a coordinate into this formula. That's the formula we're going to use. It'd be nice if I could plug in numbers that were easy to work with. In that table, which set of numbers, which coordinate there is the easy, probably an easy one to work with? The numbers are nice. Yeah?
1 and 5.
Yeah. And we're going to plug 1 and 5 into this equation. So we're going to be taking ln's of those numbers. Well, we already know what happens when we take the ln of 1. What did I get in that ln table? I got a 0. So that's going to make it very easy to figure something out. All right. So let's write that equation down. ln y equals m ln x plus ln a. And you know what? Do it over here. So ln y equals m ln x plus ln a. All right. So keep in mind the ultimate goal. Ultimate goal is to get an answer like this. That's what I want my answer to be. This equation is exactly the same thing. Okay. It's just one's written as an exponential, one's written in log form. They're the same thing. So if I can solve for a and m in this equation, it's exactly the same values of a and m in the one above it, because they're equivalent. All right, so let's fill in 1 for x, 5 for y. So 5 for y, 1 for x. Great, let's go through it. The natural log of 1. What's the ln of 1? Yeah, 0. So I get m times 0 plus ln of a. What's m times 0? 0. So this is gone. So I get the ln of 5 equals the ln of a. So I really don't have a by itself, but from this step we should be able to figure out what a would have to be. So what's a in this case? Problem? It would have to be 5, yeah. It's like, what would you plug in on the right to make it equal to what's on the left? This is 5. If you can take the ln of each side, then you can also just kind of cancel it from each side. Okay, same idea. So it ends up that a is 5. All right, so we've got one of the two things we need. We've got the a. Now, we got to use this formula again. Plug in a different point. But now we know we can plug in 5 for a. Just don't use the same coordinate again. So let's do the last one because there's no decimals. It's not really that much easier than any of the others, but you pick any point you want. We'll do that, 8/160. And plug it in. All right, so we're going to have 8/160. So ln 160 equals m, we don't know, ln of x, we know x is 8, plus the ln of 5. I don't have a lot of space, but so it's a little squished. Great. Now let's try to get the m by itself. All right. The way we're going to get the m by itself is eventually I want to get all these logs combined together. Does anyone see what I could do on the right-hand side to get ready to start combining those into a single log? Yeah? Yes. So when you want to combine logs, the first thing you do is you put anything that's in front back as an exponent. So ln 160 equals ln of 8 to the m plus ln 5. Now, I want to get a single ln. So if I was going to combine those two ln's together, we have addition. What must you have had if it's split as addition? Yeah? Multiplication. Must have been multiplication. 8 to the m times 5. Or you could say 5 times 8 to the m. That's probably how we would write it. 5 times 8 to the m. Now we have the same ln on both sides. What can you basically do with the ln when it is on both sides like that? Yeah. You can cancel it out. You can't cancel it out when you have addition or subtraction. All right? Like you can't just, I pretended to cross these out earlier. You can't do that. All right? I just did that so you could kind of see it looks like y equals mx plus b. But as long as you have all multiplication, like inside the argument, and you only have a single ln there, you're perfectly fine to cross it out. And now we get 160 equals 5 times 8 to the m. Right, and now this is kind of like the population problem. We're going to get the exponent alone. What could I do first to at least get something away from that right-hand side? Yeah?
Divide everything by 5.
Yeah, we could divide by 5. So that's a little better. That's going to be 30. Is it 32? Yeah. So 32 equals 8 to the m. And now, if you're clever, you actually don't need to change this back to a log. Okay, what you could do is 32 and 8 are both powers of what number? 2. Right? That's a little tricky. Some people might have not noticed that. But if you notice it, watch what happens. 2 to the 5th is 32. 2 cubed is 8. Right? All I did was write them in terms of the same base. And now this is kind of like a homework problem you had the other night. You had 2 expressions, and you had to write them as the same base. So that's where this problem is kind of coming from now. What's 2 to the 3 to the m? How can I just write that as a single exponent? Yeah?
2 to the 3m.
2 to the 3m. Now, it's exactly like the problem in the homework. Same base on each side, just pick a number for m that would make the exponents match. So somehow, 5 has to come out the same as 3m. So what would m be? Yeah. 5/3. So I've got m, I've got a, Now you can write your answer. Y equals ax to the m. So let's write it down. Ax to the m. The y and the x are going to stay right where they are. You're only going to fill in the a and the m. So that's the equation that would model this data. Okay, a lot of special things had to happen to make that work. Towards the end here, you had to have numbers like 32 and 8 that you could write with the same base. Right? If that hadn't happened, then we would have had to use a logarithm to solve for m. Okay. Which you could have done here, and maybe that would have been easier for some people. Just change this from exponential form to log form, like we learned yesterday. What else? Oh, also, I had to give you a coordinate that resulted in a 0. You ended up doing something times 0. If that hadn't happened, that also would have made it a lot harder. So if you ever had to do one by hand, I'm always going to make sure that these special things happen so things cancel out like that. Okay. If you notice things are not canceling and it's getting kind of weird, then you probably missed something that should have canceled out. All right, so what I want to do now is I want to type all these points in on the calculator, and I want to type in that line and see if it looks like it goes right through them. All right, actually, it's a curve. All right. So I think we did this early on, but we haven't done it in a while. So we're going to go to Stat, which is right above or right below Delete. Go to Edit. And if you have numbers in there already, just highlight the number and press Delete. And then you can clear it out. If you accidentally highlight L1 and hit Delete, it's going to delete list 1 from the calculator, so then the whole column is gone. And there is a way to get it back. I don't remember how. So I just have to reset the whole calculator, and it'll get it back that way. All right. So don't hit delete on L1, otherwise we'll just have to reset it. If you do, I'll show you how to reset it. Okay, in L1, you're going to type in your x's. 1, 3, 5, 8. In L2, you're going to type your y's. So 5, 31.2, 73.1, and 160. Okay, so now you've got the data in there. Next thing I'm going to do is turn that's like a scatter plot now. I'm going to turn that scatter plot on. So I'm going to go to second. You can do it right from this screen. You know, it's all saved. You don't have to worry about it. Stat plot. So I can do up to 3 scatter plots at the same time in different colors. I'm just going to use scatter plot 1. These two lists are what it's going to use for x's and what it's going to use for y's. I don't need to change that. I already put my x's in L1, I put my y's in L2. If I had used L3 and L4, I would have to change that right now. So on plot 1, I'm going to hit enter. And the only thing I'm going to do is turn it on. I'm not going to change the location of my x's, my y's. I don't really care about the color. The first option is a scatter plot. There's other like line graphs and stuff. So you can leave everything else. It should look just like that. So turn the scatter plot on. Now, the last thing we have to do before we graph it is make sure that we have the right window. So once you hit on, you're good. Just press window. Is negative 10 to 10 on each axis going to cover all the points I have? No. What would be a good x min? I don't want to have anything right on the edge of the screen because then I might not see part of it. Yep.
-5.
Yeah, -5, or I think even 0 would probably be okay because 1 isn't going to be right on the edge. So you could do either one. I think 10 is a good x max though. That's fine. How about a good y min? Nathan?
Probably 0.
Yeah, I think 0 is good. And for a y max, I don't know, 170. Just go a little bit higher than 160. So let's hit graph and see what the points look like. Okay. There's our points. They have a little bit of a curve to them. Now, let's type in the equation that we had and see if it goes right through the points. So y equals 5x to the 5/3. 5x raised to the 5/3. So I'm going to hit graph, and I'm going to see how good it looks. See how we did. Does it look like the equation that we calculated goes through those points pretty good? Yeah, that's a pretty good model for the data. Okay. So finding models for data, that's not really something we're going to spend a ton of time doing by hand. Okay? I'm going to show you how you can also get this equation on the calculator. So unless they ask you specifically to do it by hand, you can use a calculator to find the power model. Okay? But you can always do it by hand the way we just did. It's not really hard math, it's just you just have to remember what to do. Okay? But the math itself isn't too hard. So let me show you how to get that equation on the calculator. Well, the first step would be to go to Stat, Edit, and type in all the points. Okay, so if you want to find a power model on the calculator, step 1 is to type in the data. I'm not going to use new data. I'm just going to use the same data we already have to save time. So step 1, enter the data. Go to Stat, go to Edit, put your x's in L1, y's in L2. That's all under step 1. Okay, step 2 is once you have your data, press Stat again, and then you're going to go to Calc. So Stat, Calc. Now, let me check. I want to make sure I tell you the right one, so I'm going to check it first. And then if it works, I'll tell you what I did. That is the same equation we got. Okay, so Stat, Calc, and then you want to go down to Power Regression. Okay, it's towards the bottom, so I hit up, so then it brings me to the bottom of the list. But you can scroll all the way down till you get to option A. I don't know if I'd write option A, because if you have a different calculator, it might be a different option. But it's Power Regression. W-R-R-E-G. Okay. Click on Power Regression. You hit Enter. Now, as long as you set it up the way I told you, X is in L1, Y is in L2, you don't have to change anything. If you used L3 or 4, now you'd be changing it. So all you have to do is go down to Calculate. And then hit Enter. Now it uses different letters. We used M and A, it uses A and B, but it tells you where the letters go. So it says A is 4.99999. A is the number in front of X. Well, that's what we had. We had 5. And then it tells you the exponent. They use the letter B. The exponent is 1.66666. It's basically 1.6 repeating, which if you look at our problem and take 5 divided by 3, that is 1.6 repeating. So the calculator will not tell you it as a fraction, okay, but it will tell you as a decimal. Okay, so any questions on how I did that? The scatter plot that we turned on has nothing to do with this. The scatter plot is purely if you want to see the points on the screen. You don't have to see the points on the screen to do these 3 steps. You don't have to set the window either. Okay. Any questions on that? Now, when I did, let me just go back to what I typed in. I want to look a little closer at what it told me. Okay, is anybody's giving you more information here? Like besides just the A and the B? Do you have like an R?
Mine doesn't even show anything.
Yours doesn't show anything?
No, it doesn't.
Yours shows the same thing as mine? Alright, are you using one of my calculators?
It's a graphing calculator.
This one, okay, so I'd have to check and see, I'll take a look at it after. All right, if you see something more, and by more, I mean this. Let me just show you what it could show you. Let's go like this. All right, let me type the same thing in again. See what I'm getting now? I'm getting the A and the B, but I'm also getting this R and R squared. That's called a correlation coefficient. What that means is how well does your graph model the data? The closer to 1, the better your thing that you calculated models the data. This one is basically perfect, right? It's as perfect of a curve as you can get that fits through the data. If this R value dropped to like 0.5, that would mean it's okay, but you got some points that aren't on the curve. But we gave you the best curve we could, even though it doesn't go through it perfect. Okay, so that's called a correlation coefficient. You don't have to worry too much about it. I'm just showing you that ours is almost perfect. Okay, any question on that? All right. Right, so we'll finish up with some graphs. Now, what are the two bases that the calculator can do? It can do for logarithms base 10 and E. Well, what if I want you to graph something like this? I want you to graph base 6. Well, there's a way to do it. And this is how you do it. I'm actually showing you two ways. I would just pick one of them to remember. Either this one or this one. It's exactly the same thing. If you want to take the log of something with a base of b, and pretend b is not a 10 and it's not an e, the way you do it is you take either one of two things, the common log of the argument and divide by the common log of the base, or the natural log of the argument and divide by the natural log of the base. And I'm going to show you an example with numbers before we graph anything. So let's do log base 3 of 5. I want to know what that equals. So that's like saying 3 to what power gives me 5? Well, it's not 1, because 3 to the first power is 3. It's not 2. 3 to the second power is 9. The answer is somewhere between 1 and 2. So the way I can type this in is I can do log of the argument divide by log of the base. Remember, base, bottom. B goes in the bottom. So log 5, close parenthesis, divided by log 3. So if you took 3 to the 1.46 power, you would get 5. And what's nice is we can check it. 3 to the 1.46, I'll just round it. It's about 5, okay, because I rounded it. Right? Or, if I didn't want to use the common log, I could do the natural log of 5 divided by the natural log of 3. I get exactly the same answer. So that's how you can type a base in the calculator that's not 10 or E. Either way. I usually use the first way. Log 5 divided by log 3. All right, so let's look at a graph of this one. Can the calculator directly do a base 3 log? No, there is no button on the calculator to do a base 3 log. So I have to rewrite this as a fraction so that it doesn't use a base 3 log. What's one way that I could rewrite that so the base 3 log, there's no more 3 in the base? Yeah?
Like a fraction?
Yeah.
It would be log 10x over log 10.
Yeah, so I'm just going to write log, common log of x divided by the common log of 3. If you wanted to graph f of x, you have to type it in the way I just showed you. And I don't have to write base 10 there. Okay? Because common log, if you don't write the base, it's always assumed to be a 10. Okay, so let's graph it. And let's see what the domain and range is. I'm also going to turn off the scatter plot. So what I'm going to do is, on the y equals screen, I'm just going to press up. I highlighted plot 1, and I hit enter, and now it's off. Because I don't want to see those dots anymore. Because that data that you had is still, it's still in there. It stays in there forever, so you get rid of it. All right, so I just turned the scatter plot off. All right, so log x divided by log 3. Okay, and I'm going to start with zoom 6. All right. When we look at that graph, we've got to be a little careful. You can take the log of what kind of numbers only? What did you say yesterday? Yeah, kid?
Positive.
Has to be positive. Now, that means if I go to my table, I can pick any positive number I want. 5, 2, 1, 0.5, 0.1, 0.0001. How low is this graph going? It's going infinitely down. Does it look like it's going infinitely down from that picture? No, it looks like it stops. It doesn't. All right, so you have to be careful. The calculator cannot correctly sketch this log. It looks like it's stopping, to me, at like -2. Well, if I zoom in right there, watch what happens. Now it looks like it's definitely going past -2. It looks like it's going down, well, it's -2.5 and even further. All right, so you're changing the zoom. Now it looks better. You got to be careful. So the domain we just said is any positive number. In the range, it goes infinitely down and infinitely up. Okay? It looks like it's slowing down, and it is. The steepness is getting flatter and flatter, but it never stops going up. And I think we said this yesterday. So domain, 0 to infinity, range, -infinity to infinity. Okay. Big thing here is I just wanted you to learn how to type in a base that wasn't 10. For you. Okay. All the transformations, I keep saying this, that we've studied all year apply to logs. Okay. So without me saying it for the 6th or 7th time, can somebody tell me what A would do? What would A do to that log? Yeah, Emily?
It would shift it left or right.
Exactly. Shift left or right, opposite of what you would expect. What about B? Yeah?
Stretch it.
Stretch it? Which way? No, horizontal. The stuff inside the function is always your horizontal. So A is a short horizontal shift, B horizontal stretch. What about C? It's multiplication like B, but it's on the outside. Yeah? Vertical stretch. D. It's addition like A, but it's on the outside. So D would be your vertical shift. C and D do exactly what you would expect. Put a negative on the C or D, you reflect the graph just like always. Okay. Okay, so let's look at this. I'm comparing the log, it's not a very complicated one, just the log of base 3 negative x to log base 3 positive x. Okay, we know that negative is going to be a reflection. Which way is the graph going to reflect? Horizontally or vertically? Keep in mind, it's inside. We just said inside is always certain stuff. Yeah.
Horizontal.
That's a horizontal reflection. All right. So to get log base 3 of negative x from log base 3 of positive x, do a horizontal reflection. Okay, there's other ways to write that, however you want to think of it. You could say reflect over the y-axis. It's the same thing. All right. Now, domain, range, and asymptotes, we should be able to just think in our head what we just graphed. Okay? It looked something like this. Okay, I'll do it in a different color. Remember, it goes down forever. And now you're reflecting it horizontally, so it's going to look like this. So we should be able to get the domain and range and all that stuff just by looking at the at that quick sketch. So domain, before the domain was 0 to infinity. What's the domain now that you've flipped it? It's not 0 to infinity anymore.
From 0 to negative infinity.
And just make sure you list the low end first. So negative infinity to 0. Yep. Range? Well, the range went up and down forever before. And if you flip it, well, it's still going to go up and down forever. So range, you cannot affect the range no matter what transformation you do. And the vertical asymptote, well, remember we were getting closer and closer to 0, but do we ever reach it? No. That's why there's a vertical asymptote right there, and it stays exactly the same when you reflect it. The reason it stayed in the same spot is because the asymptote is your line of reflection. Whenever you reflect something, if a point is on the line of reflection, it doesn't move. So that's why our asymptote didn't move. Vertical asymptote is which letter? Yeah, X. A couple people on the last test when I asked for a vertical asymptote, I think they put like y equals. So it's a horizontal. Okay. And that's everything they wanted. Okay. Another transformation one. That's written a little funny. 3 minus x. How should we think of 3 minus x? Yeah?
Negative x plus 3.
Yeah, let's think of it as negative x plus 3. How many transformations are involved with negative x plus 3? Yeah? 2. So how can that be? So to sketch log 3 minus x from log x, do the following. Okay? What would you do first? And if you forget, think of the letters A, B, C, D. That's the order you do it. A, B, C, D. Yeah?
Wouldn't it be the horizontal reflection first?
Nope, because the reflection, that's B. That's going to be the second thing you do. But I do agree it is a horizontal reflection. So I'll put that as the second thing. Horizontal reflection. Now, let's look at what's in the A spot. Yeah.
Horizontal shift left.
So horizontal shift, and it's plus, so it's left. Yep. So we could say horizontal shift, or if you just say left, left means horizontal. So shift, left 3. Perfect. Okay. Any questions on that one? All right. So sketching. All right, so let's sketch a graph of a log function. Again, when you're sketching, sometimes it's helpful to find the intercepts. Not every log function has intercepts. Okay. They will always have an x-intercept because they go up and down forever. So they're going to cross the x-axis somewhere. But as far as the y-axis, if your log looked like this, it's never going to cross the y-axis. So normally you have a vertical asymptote at 0 if you don't move it at all. Once you move it, you have to find where it moves to. So to figure out where the vertical asymptote would move, all you have to do is focus on horizontal stuff. Okay. Vertical stuff doesn't affect a vertical asymptote. Think about a line that goes up and down forever. If you shift it up a little bit, it still goes up and down forever. If you shift something down that goes up and down forever, it still goes up and down forever. It's only when you take something vertical and start moving it left and right. So that's why I'm focusing on the argument. That's the left and right. That's your horizontal. So set your argument equal to 0 and solve. To find your x-intercept, you plug 0 in for y. To find your y-intercept, plug 0 in for x. We've done that. That's Algebra 1 stuff. If you need more points, you're still not sure what you're looking at, pick some other x values. Use your table on the calculator and plot them. Just make sure that the argument is positive, because you can't take the log of a negative. So like if I was going to do this problem, I would not let x be 0, or 1, or 2, or 3, or 4, or 5. I can't use those numbers. But I can start using numbers bigger than 5, and then I'm okay. Okay. So if you need more points, pick some x values, plug them in on the table, and find the y's. Or, I mean, really, you could do them by hand. You only need 2 or 3 points. So if you have to calculate them by hand using the log button, it's not a big deal. Okay, so let's sketch a graph of that. Log base 2 of 3x plus 5. And then once we sketch it, we'll find domain, range, and asymptotes. But actually, one of these things I'm going to find anyway to do the sketch, because it's helpful. Okay, log functions always have what kind of asymptote? A vertical or a horizontal? Yep.
Vertical?
A vertical. They go up forever, they go down forever. They don't ever stop doing that. But they don't go left and right forever. So there's a vertical somewhere that stops it. Okay. So let's start by finding that. How did I say you find the vertical asymptote? Yeah.
Set the argument equal to 0.
Set the argument equal to 0. So we get 3x equals negative 5. There's your vertical asymptote. X equals negative 5/3. All right, let's put that on a graph. So negative 5/3, it's helpful if you have that as a decimal. So it's about negative 1.7. So we'll put a vertical line at negative 1.7. Okay, now let's plug 0 in for x. See if we can get our y-intercept. 3 times 0 gives me how much?
0.
0 plus 5? 5. So if I plug 0 in for x, I'll write it out nice. I get log 5. And the base is 2. So figure out what that number is. So use our formula that I just showed you. Log 5 divided by log 2. So the point 0, 2.3 is on the graph. So the y-intercept is about 2.3. Okay. I already know that it's going to curve down and get closer and closer to that. Let's just get a couple more points and see what happens. Let's try when x is 2. 3 times 2 is 6 plus 5, 11, and the base is 2. So let's just type it in again, except this time I'm going to do 11, and the base is 2. So the point 2, comma 3.5 is on the graph. So 2, 1, 2, 3.5. Right, and let's do 10. Let's go all the way to the end. 3 times 10. 30 plus 5 gives me 35. So log base 2 of 35. So let's see what that is. So that's log base 2 of 35. So the point 10, comma 5.1 is on the graph. So 10, 3, 4, 5.1. It's good enough. And there's your log function. So once you get that asymptote, I only had to find 3 other points to make a pretty decent sketch. Okay, let's hit graph and see how the calculator does. Oh, I didn't type it in. I just want to see if it cuts it off, because it probably will. So log 3x plus 5 divided by log 2. Don't expect it to see it going straight down near the asymptote. It's probably just going to stop. Yeah, that's not how it should look. Okay, to me, it looks like it's going down to like about -1. If you zoom in, for some reason, zooming in, it just changes how it looks. Now, to me, it looks like it's at -3. But before, I couldn't even see that. Right? So it really does just keep going down. Any question on that? So the last thing I'm going to give you is the formula. It's a log equation, okay, and it's one of the only applications we really look at that's kind of tied to something real life, and it's to find the intensity of an earthquake on the Richter scale. So when you hear on TV like there was a magnitude 3 or a magnitude 4.2 earthquake, this is the formula that tells you that number. There's 3 variables that go into the formula for the Richter scale. R is the magnitude, so that's like a magnitude 4, magnitude 5 earthquake. A is the amplitude of the vertical ground motion in micrometers. You don't have to worry how somebody figures that out. They tell you that in the problem. So it's the amplitude, it's how much the ground is moving up and down during the earthquake. T is the period of the earthquake wave. So if you think of like an earthquake, it has a center. And the energy from the earthquake comes out as a wave from that center. The period is basically, and we're going to learn more about this when we get to it in trig, but the period is just the length of one of those waves. Okay? From like trough to trough or crest to crest, it's the same thing. It's how far apart are the waves. It's easier to visualize like if you think of waves and somebody drops a rock in the water. So how far apart are the waves' heights? And B is a factor that accounts for the weakening of the wave. What does that mean? Well, think about if you drop a rock in sand or you drop it on like a hard surface. If you drop it in sand, all the energy is pretty much absorbed. So if you have soft ground, that might absorb some of the energy from the earthquake, versus if you have granite, like rock in the ground, it's just going to transmit that energy as air. Right? So they would give you A, T, and B, and you just have to fill them in and calculate R. Okay? There will be a problem in the homework with the Richter scale, but that's the thing. Okay. Any questions on that? All right. So homework tonight, it's on 2 pages. So page 293. I want you to try 35, 43, 46, and 48. I think that was the end of 5.4. And then 301, 1, 8 through 11. 16, 23, 28, 32, 42, 52. I think it's still about the same amount of problems as normal. I think it's like 14 or 15 questions. Okay, I will be after school today if anybody needs extra help. Is anybody planning on coming at the moment? I will be here. And tomorrow we'll have our test after we go over homework.